Finite element analysis simulate how the models react to a range of environment. In this lesson, we will talk about steps that involve in finite element analysis. If you still remember the finite element analysis, it simulates how the models can react to a range of environment. We define the environment with a combination of loads and constraints, which are very important to the overall simulation. The first step in finite element analysis is the modeling. The part is model, omitting complicated geometrical features. This is the first and the most crucial step in any analysis. You will save a lot of time in rework if you model your domain correctly. So we need to pay a lot of attention to the geometry as well. Let's try to understand the reason why we are simulating the component. And this will provide you the insight to remove insignificant features from your geometry, eventually saving some computational time and unwanted complexity. And we need to remember that the simpler the model, it will be better. There is no need for unwanted, unnecessary complexity during modeling your part. The next step in finite element analysis is material definition. The material properties are defined in this step, and these material properties depend on the type of analysis that we need to carry out. Literature survey for a similar problem, it could very helpful. It could help you a lot to tackling this step. And luckily, if the material that you want to use in your simulation already exists in the material library of your finite element tool, then we can say that your job is almost done. What you have to do, you just have to select and import the material properties, and you just have to select and import the material properties from your library. And the next step is the definition of loading. This step is about the definition of external forces acting on the part of the body force by the weight of the component. And in this step, we have to be careful about force definition type in order to avoid encountering problems such as a singularity. So a finite element model will sometimes contain so-called a singularity. And this means that they are point in our model where the values tend to reach an infinite value. Singularities can be confusing because they can cause an accuracy problem inside the model, which implies a problem with the visualization because a singularity extends the range of the stress. And the major cause of a singularity is a boundary condition. And then we have a boundary condition. This step is mainly done to reduce the complexity of the problem from the engineering sense. For example, in some problem, the user might be knowing some initial condition before starting an analysis. For example, displacement of a point in a geometry, and such case fall into the initial value problem category. The main types of loading available in finite element analysis include force, pressure, and temperature. And this can be applied to surfaces, edges, nodes, and elements, or remotely offset from a feature. And the way that the model is constrained can significantly affect the result and require a special consideration. Over or under constrained models can give the value of stress that is so inaccurate that is we can say it is worthless to the engineer. So here we have an example of finite element analysis problem. We consider a 50 millimeter wide by 10 millimeter thick L shape steel bracket, like what we can see in the figure here. So this is the L shape, a steel bracket, and the bracket is bolted to a steel plate at the top hole, and a load of 7,500 Newton is applied to the bottom hole. And this is an example of under constraint model versus over constrained model. And at the left here, we have an example of under constraint model. The top hole is fixed. So the top hole here is fixed. And this allows the bracket to penetrate the plate. What we can see in the figure here. And because the top hole is fixed, it allows the bracket to penetrate the plate and thus overestimating the displacement. And this model, it does not consider the existence of a plate behind the bracket. And at the right here, we have an example of an over-constrained model. And we can see here the back face of the bracket is fixed, and this will prevent bending on the vertical part of the bracket and thus will underestimating the displacement. And here, as we can see in the figure, we have a sufficiently constrained model, and this is the better way of constraining the model. As we can see the curved line at the edge of the back. So we can see here the curved line at the edge of the back face radius is constrained horizontally in a translation X, and the top hole is fixed, and this allows the bending on the vertical part of the bracket. And here for our model here, the displacement is more realistic. So in meshing, your geometry is divided into smaller and simpler shape. And one of the purpose of meshing is to actually make the problem solvable using a finite element technique. By meshing, we break up the domain into pieces, and each piece will representing an element. So in finite element analysis, we can say that we create a mesh which split the domain into discrete number of elements for which the solution can be calculated, and the data is then interpolated across the whole domain. The next step in finite element analysis is solution. This step happens in the backend after the definition of simulation properties. So have you heard about this term before, discretization? In simple terms, it means that the partial differential equation are converted into algebraic equation. And by doing this, it will help the code to represent the equation in terms of the matrix. Matrix of the individual elements are assembled into global matrix for the entire geometry. which is then solved by solvers for the unknown variable. So the solution compute the unknown values of the primary field variable, and the computed values are then used by back substitution to compute additional derived variable such as reaction forces, element stress, and heat flow. And here we have equation of a linear static analysis. We have F equals to KD. F is the force that is usually known. Then we have a stiffness, that is the property of the material. And we have the unknown displacement. And to determine the unknown, and here are the steps to determine the unknown. First, we need to formulate the stiffness matrix for the given shape. And then we do meshing. It can be 1D, 2D, or a 3D. And then we solve the equation. And finally, we find out the unknown. And the unknown can be a displacement and a stress. And the final step in finite element analysis is post-processing. Here, after the finite element model has been prepared and checked, the boundary conditions have been applied, and the model has been solved. Now it is time for us to investigate the result of the analysis. And this activity is known as a post-processing phase of the finite element method. And here you view the result of the solution in this step, and the result can be viewed in various formats. It can be graph, it can be a value, and it can be animation and others.